Welcome to Physics Challenge. So let's look at what happens if a satellite experiencing a viscous force when it orbits in the thin atmosphere, the upper atmosphere of the Earth. First of all, we need to make some assumptions about this whole scenario. First, the viscous force, let's assume it takes form of AV to the power of gamma, and V is the velocity of the satellite, and the A and gamma are constants. So we can think this viscous force as some resistance force experienced by the satellite when it orbits the Earth in the atmosphere. Second, since there is an external force applied on the satellite, so the satellite will drop to a smaller orbit over time. What does it mean is this. So over a certain period of time, we don't know how long it is, but we know the change between the larger orbit to the next smaller orbit is the r. And let's assume the rate of change in the radial distance r is constant, given by dr dt equals minus k. So, and the k is a positive number. And most importantly, we assume the rate of change which is k, is sufficiently small so that the loss of energy per orbit is small compared to the total kinetic energy. And then the goal is to find an expression for this viscous force, aka what are A and gamma. So before we jump to the answer, you can think about it. Do you think gamma depends on the mass of the Earth or the mass of the satellite? Do you think A depends on those? So let's denote E as the total energy of the satellite when it orbits the Earth in the atmosphere. So the only external force experienced by the satellite is this viscous force. So the change in total kinetic energy is only resulted from this viscous force. So dE over dt is the power of this whole process, which is Fv, recalling the formula of power. So what is F? F is this force, which is Av to the power gamma, and times V, we have Av to the power of gamma plus 1. So what is V? So in a certain period of time, the orbit doesn't change. So the radial distance remains the same. And we had this equation, which is the centripetal force equals the gravitational force. And then find the expression for V, which is square root gm over r. And we plug into our first equation, we find the first expression for dE over dt. And recall that we also have a quantity which is dr over dt. So how do we relate dr over dt to dE over dt? Which is very simple. And we just say dE over dt equals c over dr times dr over dt. So dr cancels out. So it's a smart way to rewrite dE over dt so that we can use the value of dr over dt, which is given. And then this way, we find out dE over dt equals minus k times dE over dr. So what is dE over dr? Remember E is the total energy of the satellite. So what is the total energy? It has two components. The first component is the kinetic energy of the satellite, and the second one is the potential energy of the satellite. So for the kinetic energy, it's definitely 1 over 2 times mv squared, which is the standard formula for kinetic energy. And we plug in V, we get that kinetic energy expression. And what is the potential energy? It's minus gmm over r. Remember the equation F equals negative gradient U, which is the potential energy. So in this case, the gradient is just the first derivative of the potential energy, and F is the gravitational force. So we can integrate the gravitational force to get the potential energy with respect to r. And so in the end, the total energy is negative gmm over 2r. And therefore, we get the second expression of d over dt. And apparently, these two expressions of d over dt are the same. So in the end, we can equate these two together to find the final expression here. And we can observe this equation, and we notice that the only variable that is changing over time is this radial distance, r, because the orbit changes. So we have to cancel out a changing variable because to make sure this equation is established. And to make that possible, we have to make sure gamma equals 3. So gamma doesn't depend on any other quantities, the mass of the Earth, no. And then we find the expression for A after plugging in gamma equals 3. So finally, we arrive to the final expression of the viscous force, which is minus km over 2g capital M v cube. So thank you for watching. If you like the content, please subscribe, like, and comment below. See you next time.